Fukushima, 3 Mile Island, Chernobyl, Fat Man and Little Boy. All very chilling names to utter. It doesn't matter what generation you identify with. Young or old, we can all point to at least one infamous nuclear device that failed in the case of power plants, or functioned in the case of weapons, with catastrophic consequences. Since 1945, the phenomenon of nuclear fission has been used to release large quantities of energy, sometimes in slow, controlled, sustained conditions to create electricity for civilian use. Other times in short, instantaneous bursts of energy to produce stunning devastation in military applications. We're deep into our tour of matter, its properties, and how scientists and engineers characterize and use those properties to change the world around them. From acids and bases to electrochemistry, we've carefully explored the forces that hold multiple atoms together in chemical bonds. We considered the electromotive force, which is essentially a measure of how tightly held electrons are by nuclei that they orbit. But today we're going to change our focus yet again. Today we're going to come dangerously close to trespassing on the territory of particle physicists. The energy stored in chemical bonds is awesome. But make no mistake, chemical bonds can be used to store and release really large amounts of energy. But the energy involved in the making and breaking of chemical bonds pales in comparison to a different kind of energy. The energy that holds nuclei together. It's this energy, known as nuclear binding energy, that powers nuclear reactors, weapons of mass destruction, and even our own sun. So instead of focusing on the building up compounds by bonding atoms together, this leg of our journey together is dedicated to better understanding, building up, and breaking down the atomic nucleus itself by adding and removing subatomic particles. Let's begin with a quick review of the structure of the atom. Recall that atoms are composed of a dense central nucleus made from protons and neutrons, particles that we collectively call nucleons. The protons give the element its identity. For example, 2 protons in the nucleus means you're dealing with helium, regardless of how many neutrons may be present. The neutrons give the nucleus additional mass without changing the identity of the element. So helium with 1 neutron has a total atomic mass of 3, while helium atoms with 2 neutrons would have a mass of 4. We call these 2 atoms isotopes. In this case, both are stable, both are found in nature, although helium-4 atoms are far more abundant, comprising all but about 1 in a million helium atoms. This relationship extends to all other elements. For example, carbon-12, carbon-13 are both found in nature. Each has 6 protons, making them both carbon nuclei, but carbon-12 has only 6 neutrons, while carbon-13 has 7. Even larger elements like uranium have multiple isotopes. Uranium-235 has 92 protons and 143 neutrons, while uranium-238 has 92 protons but 146 neutrons. Both are uranium nuclei and will bond and behave chemically in very similar ways. But when we step down to the level of nuclear changes, these 2 uranium atoms behave very, very differently. To distinguish isotopes, nuclear chemists write their elemental symbols with 2 numerical notations preceding them. The top number indicates the total mass of the nucleus, and the lower indicates the total number of protons in that nucleus. In 1895, William Röntgen, a German physicist, discovered a very unusual phenomenon. He found that by passing electrical current through a coil inside of a very powerful vacuum, he could create a type of electromagnetic radiation that could expose photographic film and penetrate many different materials that ordinary light did not. Uncertain of what to call this radiation, but equally certain that it was a groundbreaking observation worthy of reporting in the scientific community immediately, Röntgen described his new discovery as X-rays. The following year, a French physicist by the name of Henri Becquerel was conducting experiments with uranium-containing compounds. He'd been exposing these compounds to light, then placing them in a darkened room and exposing them to photographic paper in an attempt to prove a theory. The theory was that X-rays were re-emitted sunlight, somehow changed by the uranium. It's an interesting theory, but one that was undone by something as simple as a cloudy day. You see, when Becquerel had no sun available to expose his uranium to one day, he did what any good scientist would do. Rather than waste his day, he conducted a control experiment, removing the sun from the equation and exposing the photographic paper to his uranium compounds anyway. To his surprise, the film still showed evidence of exposure. His theory was crushed, but his place in history was secured by this observation. Becquerel had shown that the radiation was a result of some intrinsic process within the uranium nucleus, not the re-emission of stored energy from elsewhere. Uranium atoms had the ability to emit some sort of radiation all on their own. Radioactivity had been discovered, and Becquerel had punched his ticket to the Nobel Prize, which he received in 1903, along with Marie and Pierre Curie for their research into this newly discovered phenomenon. In fact, the radiation that he discovered was not X-ray radiation. He knew this because he discovered that passing a beam of his newly discovered radiation through an electromagnetic field caused the beam to bend into two, as though some of the particles making it up were positively charged and others were negatively charged. Now, once he had this realization, Becquerel used his technique to discover that many different materials had this ability to emit beams of particles that could expose photographic paper. Not only that, but some emissions were positively charged, some negatively charged, and some not charged at all. Some materials emitted only one of these types of beams, while others emitted some or even all three of them. Clearly, there was a process fundamentally based on the atomic structure of these elements that determined how they decayed and which types of radiation they produced in doing so. We now know that what Becquerel had discovered in his earliest experiment was actually not electromagnetic radiation at all, but a radioactive decay product. Small pieces of the uranium nucleus that had been ejected as it reordered itself into a different, more stable arrangement. So, what are the three types of radiation that were observed in Becquerel's experiments? What exactly were they? Well, the answer to that would take some time, but clues were offered in the experiments of Ernest Rutherford. You may remember that Rutherford's most famous for his model of the atom, developed when he demonstrated that atoms are mostly empty space. You may also remember that he proved this by firing the nuclei of helium atoms at a piece of gold foil. But Rutherford was already a Nobel laureate when he conducted those now famous experiments, and that proposed his model of the atom. But Rutherford's original stroke of genius, though, the one that earned him his prize, was to note that the radiation beams observed in Becquerel's apparatus had not only differing charges, but varying ability to penetrate aluminum. Rutherford repeated Becquerel's experiments, but successively placed layers of aluminum foil into the apparatus between the uranium radiation source and the photographic paper acting as a detector. He noticed that when he did this, he observed that the positively charged radiation didn't penetrate the foil as well as the negatively charged radiation, and neither of those could match up to the penetrating power of the uncharged radiation. Now, Rutherford named the positively charged radiation alpha radiation, and the negatively charged beta radiation. The third type, the uncharged, we call gamma radiation. So Rutherford and Becquerel, and others like them, had determined the alpha, beta, and gamma radiation's charge and masses in some of their makeup, and actually their source, uranium-238, is an excellent example of how these three types of radiation play in nuclear chemistry. So let's take a look at that. Let's start with a nucleus of a uranium-238 atom. And we're going to first see what happens when alpha radiation takes place. Now, this is actually the correct number of neutrons and protons. You don't have to count for yourself. Take my word for it. There are 238 total nucleons here. Now, what happens in an alpha radiation event is that helium nucleus breaks loose from the uranium atom. So that's the source of your alpha radiation right there. So anytime a helium nucleus is emitted, you're undergoing an alpha radiation. Now, interestingly here, you probably noticed this, that I put the atomic numbers next to these elemental symbols, even though the elemental symbol itself tells you what the atomic number should be. And it might seem redundant, but the reason I've done it is that we want to be sure that we give ourselves a reaction we can look at and scan for charge balances. Because just like we did previously with chemical reactions, we've got to keep things balanced. Now, in this alpha decay process, I've maintained my charge balance. 92 total protons at the beginning, 92 total protons at the end. Additionally, of course, we have the mass of each, and that allows us to scan quickly for mass balance, which still has to hold when it comes to the nucleons themselves. And again, I have that 238 in my uranium atom, and then 234 in my byproduct, and 4, of course, for my alpha particle. So we can scan through any reaction that we write and double check ourselves to be sure that we've got it right. Now let's take a look at the beta radiation that emits from a uranium-238 nucleus. Now in this case I'm going to go to the byproduct, and that's thorium. So our uranium-238 has just undergone alpha decay, and now it's thorium-234. A thorium-234 can undergo a secondary decay, and that decay involves beta radiation. So I'd like to call your attention to one particular nucleon here. Okay? Now that I've got my thorium-234, it itself is unstable. And one of those nucleons, in particular a neutron, is going to eject a negatively charged particle, an electron. And in doing so, become a proton. So the emission of beta radiation robs my nucleus of a unit of charge. In other words, it brings it up to a palladium nucleus. Right? Because I've lost a negative charge, I've net gained a positive charge. In other words, I've turned a neutron into a proton. The result is my palladium decay product and my beta radiation. Now, a third type of radiation that Rutherford discovered was, of course, gamma radiation. Now, the gamma radiation that comes from the uranium-238 sample is associated with that first decay process that we looked at previously, when our uranium-238 loses an alpha particle. But in this case, once that alpha particle has been emitted, I have now a thorium nucleus. And what that thorium nucleus is going to do is have to rearrange itself. Okay? Because we've removed 4 nucleons, the remaining nucleons will have to shift in order to find their lowest energy conformation within the nucleus. And when that shift happens, you'll notice that a bit of light is ejected, just the same way that it is when electrons in an electron cloud rearrange. When nucleons within the nucleus rearrange to try to find a lower energy state, they emit light. Now the difference is that the energies we're talking about are usually much, much higher than the energies associated with the transitions within the electron cloud. So my photon that's emitted is of extremely high energy, such high energy that it falls into the gamma ray class of electromagnetic radiation. Nonetheless, it is, in fact, light. It's a photon. Now, even though the alpha, beta, and gamma decays are what we usually talk about in terms of nuclear decay, there are lots of other players in the process, more so than just those 3. 2 very common processes that we'll have to understand to get through our lectures on nuclear chemistry are electron capture and positron emission. And an excellent example of both of these processes, in fact, is the decay of carbon-11 to boron-11. Now, carbon-11 is a fairly uncommon nucleus. You don't find it in nature. But when you do make it, or isolate it, it tends to decay into boron-11. Now, you can get to boron-11 one of 2 different ways. In our first example, we're going to have our carbon-11 nucleus capture an electron, and in doing so, cancel the charge of one of its protons, turning it into a neutron. So we've converted carbon-11 to boron-11 through the capture of an electron. Now, another process that takes place sometimes is the positron emission. In this case, rather than capture an electron from outside, our nucleus is going to emit a positron. So by emitting the positron from one of the protons, again, we've converted that proton into a neutron just as we did before. But in this case, we've emitted a positron. So we have to be ready to look for both types of radiation when it comes to the conversion or the radioactive decay of carbon-11 to boron-11. And in fact, what I've just shown you now is only a very small sampling of the types of particles that you can expect to see playing in these kinds of reactions. In fact, you'll see things like alpha particles, of course. You'll see beta, and you'll see gamma, which is high-energy light, or photons. But we'll also be dealing with things like positrons, which carry positive charge but essentially no mass. Neutrons, which carry mass but essentially no charge. And even protons will start to move in and out of nuclei as things start to get advanced for us. So keep in mind that these are just some of the players in this dance of nuclear radiation and reactivity that we'll be looking at later on. So now we know that alpha radiation is made up of helium-4 nuclei. Beta radiation is made up of high-energy electrons ejected not from the cloud of an atom, but from the atom's nucleus itself. And gamma radiation is high-energy electromagnetic radiation, resulting from transitions in the structure of the nucleus itself as it relaxes after a nuclear reaction. As uranium-238 decays, another dozen or so alpha and beta decay steps will take place before we arrive finally at lead-206, the first truly stable atom in that process. Here is where the decay of uranium-238 will stop. Electrons and positrons are nearly massless compared to nucleons. So losing or even gaining one doesn't change the mass of a nucleus, but it does change that nucleus's identity, effectively adding or removing a proton depending upon the process, and promoting a rearrangement in the nucleus that emits gamma radiation. Electron capture is the process that takes place in the formation of neutron stars. As large dying stars collapse, pressure increases in the core of these stars, and the pressure can become so high that protons themselves collapse, capturing their own orbiting electron and becoming a neutron instead. Now, with no electron cloud, neutrons have a much smaller radius than hydrogen atoms do, explaining how neutron stars can achieve their densities of about 100 trillion times the density of Earth. So why does all of this happen? Why do some atomic nuclei decay or transform over time while others don't? Well, atomic nuclei are very challenging structures to understand. With all of the electrostatic repulsion going on between and among positive charges in the confined space of an atomic nucleus, how is it that they stay together at all? Now, the answer to this question is as fundamental as it is elusive. No one really knows exactly why. But there are a few general trends in the stability of nuclei based upon the number of protons and neutrons that they contain. In general, nuclei with 2, 8, 20, 28, 50, or 82 protons somehow tend to be more stable. The same numbers apply to neutrons with 2, 8, 20, 28, 50, 82, or even 126 neutrons being somehow more stable. There also is a strong tendency for there to be an even number of protons, neutrons, or both in stable elements. In fact, of all known stable isotopes, more than half have an even number of both protons and neutrons. Possibly even more surprisingly, only 5 of 265 known stable isotopes have an odd number of both protons and neutrons. Now, that information alone isn't enough to crack the code of how nuclear structure affects stability, but it's more than enough to compel us to the assumption that nuclear structure does matter. Having even numbers of nucleons imparts stability somehow. There are other trends in stability as well. If we create a chart with the number of protons on the x-axis and the number of neutrons on the y-axis, all known stable isotopes fall here. Quite an interesting trend, isn't it? As stable isotopes get larger, the ratio of neutrons to protons grows predictably, creating a curved region of the plot commonly known as the zone of stability. This gives us a cursory tool for the prediction of how a given unstable nucleus might decay. For example, nuclei above the zone of stability, like iodine-131, can move toward the zone by emission of a beta particle, stepping from left to right on the diagram toward the optimal ratio. In contrast, isotopes below the zone of stability need to increase their neutron-to-proton ratio. This can be accomplished by positron emission or electron capture. One very common example of this is the element fluorine-18, which decays primarily through positron emission. Elements larger than lead have no stable nuclei at all, and their quest to lose mass will often lead to the emission of alpha particles. A great example of this, of course, is the decay of uranium-238, which, as we discussed, undergoes not just one, but actually 8 different alpha decays on its way to becoming lead-206, squarely in the zone of stability. We're all familiar with the potentially toxic effect of radiation exposure. It's widely believed to have been the culprit behind an early demise for many great scientists who made some of the first discoveries in this field, such as Marie Curie. And of course, we are nearly all aware of the adverse health impacts that can be caused by overexposure to radiation from reactor meltdowns or nuclear weapons fallout. But radioactivity isn't all bad. Recall that shortly after its discovery, Bertram Boltwood used it to estimate the age of the Earth, launching a quest to understand how our solar system and galaxies formed. And thankfully, some keen minds like those of Curie quickly realized that the high energy content of radiation might actually make it dangerous in high uncontrolled doses, but might also make it useful as a medical tool when properly harnessed. In fact, Curie is widely recognized as the world's first radiation oncologist, as it was she who realized that directed radiation could be used to kill cancer cells in humans. Clever use of radioactive nuclei has led to the development of certain cancer therapies. For example, iodine-131 is a radioactive isotope of iodine that emits potent beta radiation, which can cause cell death. It's easily made in the cores of certain nuclear reactors as a byproduct of fission processes that we'll be discussing later. Now, iodine itself tends to accumulate in the thyroid gland. Healthy individuals, of course, would rather not have radioactive thyroids. So when nuclear accidents like the infamous Fukushima reactor breach happen, locals are encouraged to take in large doses of non-radioactive iodine-127 to be sure that they flush out any radioactive iodine that may have gotten in. But what about thyroid cancer patients? Physicians sometimes will deliberately dose their patients with iodine-131, which accumulates in the thyroid and incorporates itself into the rapidly growing cancer cells there. These cells then irradiate themselves from the inside out, slowing their growth or even killing them outright. And the 8-day radioactive half-life of this isotope makes it ideal for a short-term cancer therapy, as its effects will wear off over about a month or so naturally. And the use of radiation in medical therapies extends far beyond simply using it to kill localized cancer cells. The high-energy particles that it can create and its ability to change the very identity of the element emitting it can be used in a number of positive ways. For example, fluorine-18 is often used in the medical technology community in a technique known as PET scanning, which stands for positron emission tomography. This technology is very useful in the detection of certain cancers, since fluorine-18 can be artificially introduced into the patient by giving them an injection of fluorodeoxyglucose, a molecule which chemically resembles the same glucose that your body uses to manage energy. But it has a single oxygen atom replaced by a fluorine-18 atom. As this material is taken up by growing cells, the concentration of fluorine-18 in those cells will increase. And as you might guess, cancerous cells that are growing particularly quickly tend to take up more of this molecule than the surrounding healthy tissues do. PET scanners then look for characteristic radiation that accompanies the positron emission of the fluorine-18 atoms as they decay into harmless, stable oxygen-18 atoms. Fluorine-18 is perfect for this application for several reasons. First, of course, is that it can be substituted for an atom on glucose and then harmlessly decay into an actual molecule of glucose that's not toxic to the body. Second, the half-life of this positron emission is just under 2 hours, perfectly suited to a procedure in which a patient is dosed and scanned in a single afternoon. By supper time, the fluorine-18 isotope is practically gone from their system. But none of it would work if the fluorine atom in this medical marvel were not compelled to decay in a quest to reach the zone of stability as oxygen-18. So let's summarize our discussion on radioactive decay. We started at the very beginning with Becquerel's realization that certain isotopes of certain elements radiate energy in some very useful ways, and that they do it all on their own in a spontaneous, internal process. We saw how Becquerel proved this by exposing photographic films to uranium salts in the absence of light, only to find that the silver salts in the photographic films had undergone a reaction even though they had never been exposed to visible light. We saw how Becquerel and Rutherford determined that alpha emission involves the loss of a helium-4 nucleus, how beta emission involves the loss of a high-energy electron from the nucleus. Additionally, we accounted for gamma radiation, which consists of high-energy electromagnetic radiation that can accompany these kinds of processes. We also considered the phenomenon of positron emission and electron capture processes, by which protons can convert into neutrons, altering the identity of elements and even turning hydrogen atoms into bare neutrons, the likes of which make up neutron stars. Next, we looked at trends in nuclear stability, and we saw how the so-called zone of stability in the neutron-to-proton ratio of elements can be used to predict not only which isotopes of a given element will be stable and which will not, but also to forecast exactly how each isotope will decay in its quest to form a stable nucleus. Finally, we explored one of the more influential uses of radioactive decay in the modern world, medical technologies. We saw how the beta decay of iodine-131 can be used for targeted delivery of radiation therapy to tumors in the thyroid, and how positron-emitting fluorine-18 can be used to locate tumors in the body. But we have only started on our investigation of nuclear chemistry. Our discussion covered most of the processes by which atoms can radioactively decay as a means of reaching a more stable state. But we've not yet considered the energetics of those processes in a quantitative way. We'll remedy that next time as we put some numbers to the incredible forces involved in holding the atomic nucleus together. Although it's more the realm of physicists, the synthesis of new super-heavy elements is of course always of interest to chemists. Now, when most of the new super-heavy elements are made, they only survive for a fraction of a second, and only a few atoms can be created at any given time. This makes them very difficult to observe. So physicists often don't directly observe those super-heavy elements, but instead they observe the processes by which they break down and then back-calculate the fact that they must have created what they had hoped to. So let's put that in a little bit of context with a challenge problem. In 2016, the International Union of Pure and Applied Chemistry, or IUPAC, confirmed that element 118 had been created actually more than a decade earlier. It took that long to confirm that this had been done successfully. Now, in the experiment, a new, as of yet unnamed element called ununoctium for the moment was produced, but it wasn't directly observed. Yet the scientists knew they had created ununoctium-294. Now, how did they do that? Well, what they did was they used the sequential alpha particle emissions to confirm what they had made. They were simply looking at decay products. So, to that end, let's think like these scientists here. Let's write out the 3 nuclear reactions corresponding to those first alpha particle emissions from ununoctium-294. We'll begin again with ununoctium, which has an atomic number of 118, and it has an atomic mass of 294. Now, the first alpha emission would have created, of course, an alpha particle and another element which had lost 4 units of mass and 2 protons, decreasing its atomic number by 2. This corresponds to element 116, specifically livermorium-290. Livermorium-290 only exists for a fraction of a second itself before it undergoes yet another alpha decay, creating another alpha particle and a new element that is again 4 mass units lighter and has 2 fewer protons. This would be an atom of flerovium-286. And if we continue, we find that an alpha emission from flerovium-286 should lead us to an element called copernicium-282, which then undergoes a spontaneous fission process whose products can be directly observed. So, by observing 3 alpha emissions and then the products of the fission of copernicium, we were able to demonstrate that ununoctium had actually been created.